So another issue that we observed and that we would like to address, again, this is regarding efficiency, is that the policy often converges long before the state values. This is regarding specifically value iteration algorithm. So as we've seen in the example before with the small grid domain, the policy, so here you can see the policy as these small arrows. These small arrows are the policy that will be extracted if you run an argmax sweep over the state space, given the current values. So for each iteration, if you use these current values in order to compute the optimal policy, these are the actions that you will obtain for each one of the states. And you can see that at iteration 10, we already converged on the optimal policy, right? The policy itself does not change even after 90 more iterations. However, the state values do still converge, but it doesn't matter. It doesn't matter for the policy. So the policy converged far before the state values did, and the policy is actually what we care about, right? So there was no, after 10 iterations, there was no need to perform 90 more iterations. In this case, in order to compute the optimal policy, right? If you would like to converge on the correct V star values, then maybe you would like to continue these value iterations, but usually what we care about is converging on or computing the optimal policy by star, and for that we did not need to continue until iteration 100. However, it's not straightforward to know, to infer when the policy has converged, right? Even though the state values have not converged yet, it's not straightforward to say, okay, at this point the policy will not change anymore. Although we would like to do that, of course, right? So one solution that we'll see to this issue would be to converge directly on pi star. So what we're going to do is to compute a policy and improve the policy in iteration until we reach the optimal policy. This is known as policy iteration. And again, we're going to see now the basic approach for policy iteration, and later on we'll take this approach, we'll advance it further ahead, and we'll combine policy-based approaches with value-based approaches to get state-of-the-art RL solutions. So how would policy, the very basic policy iteration, how would that work? So the idea here is to compute state values, but not the optimal state, not the state values for the optimal policy, not V star, but some V pi for some initial policy. Okay, we calculate the state value for some fixed policy. Again, it can be arbitrarily initialized, the policy. And so it's not necessarily, or in most cases, it will not be the optimal policy, right? So V pi, the state value for a specific policy, is different than V star, than the state values for the optimal policy. So you might ask yourself, well, why would I want to compute V pi if I'm not really interested, if I can gain much more from computing V star? The answer is that V pi is actually much easier to compute, substantially, and I'll show you that in a second. Once we compute V pi for some intermediate policy that we have, we update our policy using one-step look-ahead as before with the argmax, a Bellman update over the entire state and action space with a one-step look-ahead, and we choose the best, or we set the best action at every state based on the action that maximizes the expected sum of reward for the specific policy, right? So these are, I'm computing the optimal action based on the V pi values, not on V star. So again, we update our policy not necessarily towards, or it will be towards, but we won't necessarily after a single update get to pi star. But as a matter of fact, we will get closer to pi star. We guarantee to get closer to pi star, or reach pi star, which would be a fixed point. I'll show it to you in a second. then we repeat this process. So now we have an updated policy, and again we compute vpi for this new policy, and repeat the process and update pi and continue. And we continue this process until convergence. That is, until we reach the optimal values, V star, which imply the optimal policy. This approach is guaranteed to converge to pi star. Okay, in the tabular case, but for now we're only discussing a tabular case. Tabular case means that we store the state values and the state policy and one action for each one of the states in a very big table. Okay, this is as opposed to value approximation or policy approximation, where we'll use something like a deep neural network, where we'll just push a state as input and it will give us some output and we'll have to tune that output. But that's a whole different can of worms that we'll get to later, of course, when we discuss deep reinforcement learning. In the tabular case, everything is much more tidy and neat, and we can actually prove some convergence guarantees, as is the case for policy iteration. So, moreover, it's not only that this process is guaranteed to converge eventually, it's actually guaranteed to improve in every step. That is, the policy between iteration must improve monotonically with the iteration number. Same goes to the state values, of course. And so at each iteration we will improve the policy unless we reach the optimal policy. At that point we will be at a fixed point, right? So we won't be able to improve over pi star, but if we observe that we did not improve our policy at a specific iteration, this implies that we converged on pi star. So we have a specific rule telling us when our policy has converged, right? So now going back to my initial claim, I said that it makes sense for us to compute V pi instead of V star and do it over several iterations because computing V pi is much easier or much faster than calculating V star. And why is that? Any idea?
That's because you just need to learn the value of the state and not for each action, which would be more work.
Because I'm fixing the action, right? So before I used a Bellman update where I iterated over all possible actions. Which action returns the maximum value? And that is, taking a max operator is highly non-linear. Now, when I consider a specific policy, I'm telling it that I'm considering only a single action. And that helps me reduce or turn the non-linear Bellman equation into a linear equation. Okay, and now, what's so good about linear equations? Well, I can use a linear solver, right, to efficiently solve them. So I get rid of the non-linearity, the max operator over all of the actions. And now I get a linear equation, and I get one linear equation for each one of the states in the state space, right? So I have a set of linear equations and a set of unknowns, right? And so this can easily be solved with a linear solver, right? It can be very efficiently. And a linear equation, solving a set of linear equations can be done in a complexity of S squared, where S is the number of equations, or in our case, we'll have one equation for each one of the states in the state space. Specifically, by the way, you will be implementing policy iteration in your home assignment. So NumPy in Python actually provides us with a built-in linear equation solver known as, well, linalg, and you can run a dot solve on it, and it will solve you a set of linear equations. So you will have to implement that in your home assignment, and you will have to use this function in NumPy. Okay, I do suggest reading the documents for this solver, for the linear equation solver, because there is a specific way it requires you to represent all of your linear equations. Okay, as a matrix and as a vector of the variables, and you just provide the matrix and it will give you the solution. Question, yeah?
So Professor, we currently study two methods to get a policy. One's a policy iteration, where we can directly learn the policy, and one is Q-learning, which makes it easier to extract the policy as alternatives to value iteration.
Right.
In which scenario would we want to use which one to get the policy?
So that's a complex question. I'll show you some results for some domains. We'll do some very high level analysis, but so I'll just say that there are pros and cons to using value-based solvers compared to policy-based solvers. And we'll actually have to analyze each one of these pros and cons, because later on we'll try to combine different types of solvers in order to address or to have the best of each and to address the shortcomings of each. Okay, so we'll have to, this is a much larger discussion which we'll perform later on. Once we introduce also function approximators, there are also more complications, but this we'll need to discuss that in a higher level context. For now, I just want to learn the basic algorithms, okay? And later on we'll discuss how and when to apply each one of those. And by the way, in your home assignments, you'll also get a feeling of when each one works best, because the algorithms that you're going to implement are general. That is, you'll implement them once, and then specifically if we use OpenAI's Gymnasium, you can easily load different domains, and your solver should work on all of them. With some caveats, right? There are some caveats. We'll discuss those later, but usually you'll have several domains that you'll be able to test for each one of your implementation, and then you'll be able to see how they work differently in different cases. But let's delay this discussion for later. Okay, so how would that look? How would the linear set of equation look if you didn't get it? So let's look at a specific example, and actually this is the specific example that we've seen previously, the simple grid environment from I think this is from UC Berkeley, right? The UC Berkeley course. So for each one of the states in our environment, for instance, for state V11, let's say this state here, coordinate 1, 1, we have a specific policy that we're computing the values for, right? And let's say the policy that we are considering is the policy that is provided here. And again, this is a tabular policy, meaning for each one of the states, it tells us, we store a specific variable that tells us which action to take. Okay, so let's say these are the actions that we're going to take. And now, as we discussed previously, our Bellman equation simply becomes a linear equation. And we said that we have a probability of 0.8 for actually succeeding in going north, in going in the direction that we intend to. And we multiply this by the immediate reward, which is -1, the battery drain, plus 0.95 times the state value in the next state, right? Which is an unknown in this case, but our linear set of equation will tell us the solution for that value as well, right? We have a definition for it. And then we also need to factor in the probability of slipping to each one of the sides, right? We have a 0.1 probability of arriving at this state and a 0.1 probability of staying in the same state. But now, as you can see, we have S on the side of the state space unknowns and the same number of equations. Okay, one outlier or two outliers would be the terminal states that are simply assigned with the immediate reward, right? These are terminal states, these two here on the right, and so they are assigned a -1 and 1, just the immediate reward. Okay, so at the highest level, the policy iteration works as follows. You start by coming up with a policy, it can be arbitrary policy, right? Ask our robot to decide on any policy, so it chooses a policy. Then we ask our linear solver library to examine the policy or provide the state values for the specific policy, and this can be done pretty effectively with the specific library that we discussed, the linear solver. This provides us with specific state values, V pi values, which we then use to perform one full sweep in order to compute the optimal policy for these given values. And the process continues until the policy does not change anymore. That is, between two iterations, we remain with the exact same policy. This is guaranteed, then in that case, it is guaranteed to be the optimal policy by star. Okay, so let's discuss the similarities and differences between the two approaches that we already went over. So both in value iteration and in policy iteration, value iteration can refer, by the way, to both the Q value and the state value. And again, the state value and Q values and action value, Q values are also known as action values. They can be easily interchangeable, right? So both approaches, both policy iteration and value iteration, compute at the end of the day the same thing, right? They compute optimal state values, or they result in the optimal state values. In value iteration, every iteration updates both the values and implicitly the policy. So any set of values, any value assignment can imply a specific policy. We don't track the policy, we just converge on the state values, but taking the max or the argmax over actions implicitly defines that policy, right? And if we converge on Q values, then it's even simpler than that. In policy iteration, we do several passes that update utilities for fixed policies. Each pass is fast because we consider only one action, not all of them, right? So we get rid of the nonlinearity in the Bellman equation. After the policy is evaluated, a new policy is chosen, and this requires us to do a full sweep over the state and action space. This will be slow like in value iteration, like a one value iteration pass. But now the new policy will be better, or if it's not better, then we're done. Right? If it's the same policy, then we are at a fixed point, meaning we have converged on pi star. Okay, so both of these approaches can be computationally intensive, but in many times policy iteration will converge faster on the policy. That's actually, okay, it's a bit more settled than that. Policy iteration will, in many cases, will much faster raise a flag and tell you converged, right? That it already converged on the optimal policy. Value iteration might converge on the policy very quickly, but it will never raise a flag and tell you I've converged. Okay? And you will implement both of these algorithms, so you'll actually be able to see that. You'll be able to see that value iteration might take some time to converge on the values, but not necessarily so on the policy, and so policy iteration will converge or will terminate much quicker.